In this video, I'll be deriving an equation for maximum angular frequency. A cylindrical cup can be rotated without a specific volume of liquid inside being spilled. So we'll have a cup that looks like this, how I've drawn it. And the cup has a radius r, a height h, and then a fluid inside with height r as well for simplicity. And when we spin this cup, the fluid is going to take this parabolic shape, or at least the fluid line will turn into kind of a parabola. And we can say that we are turning this cup with an angular frequency. So what we want to solve for is what angular frequency can we rotate this thing before the liquid spills out. So the first thing that we need to know is that the change in pressure with respect to radial position, small r, is equal to density times centrifugal acceleration, which is the angular frequency squared times the radius. So I'm going to take that equation first. And we're going to derive it from 0 to a final pressure, because we're going to assume that the external pressure, the pressure of the surroundings in this system, is equal to 0 atmospheres. So I'll go ahead and draw that into this picture. Or 0 pascals, sorry. So then we can say this. And, well, this will be small r. And from here, we can just evaluate. So on this side, and from this, we get that the final pressure is equal to the density times that angular frequency squared times the radius squared over 2. Now, we also know that pressure is equal to the density times gravity times height. So then we can set those two equations equal to each other. So the densities cancel, and we get that pressure is equal to, or excuse me, so we get that for the height, because that's what we want, really. Is equal to this. So now we have an equation for the height of the liquid relative to the lowest point, which is the dip, because we evaluated that first equation from 0 to a final pressure and 0 to a final radius. So the radius is 0 at the middle of that circle of the cup of the cylinder, and also at that radial position of 0, right in the middle, is where we have that dip. So now we have this equation, and when HR is equal to 0, that's where we have the height of the dip. And then where HR is equal to the full radius, that's where we'll get the height of the liquid at the edge of the cup. So right here. Okay, so now that we have that, we want to solve for the angular frequency at that point. And we can find the dip by using this equation. And this volume is just the volume of the liquid that's above the dip when we're spinning it, and it's at that point that we want it to be. So I'll draw that out. So this shaded volume is the volume that's equal to the dip times the radius squared times pi. So if we look at this shaded area from the side, it looks like this. And if we look at it from the top, it looks like this, where that inner circle is whatever radius we decide. So if we take it into a bunch of smaller pieces or smaller intervals and we look at it that way, we can do this, which looks like this. And we can use the circumference equation to find the change in volume with respect to the radial position. So since we know that circumference is just equal to 2 pi r, we can do the change in the volume with respect to the radial position like this. And technically for this, it'll be small r, since again, that's our radial position and we're looking at it in intervals. So then we can derive this, or integrate it, I should say. And we want to do that from 0 to the total radius of the cup. And then we can use our equation from up here and sub that in for h. So then this will give us and again, that radial position variable will stay on the inside since that's what we're integrating. And then we can evaluate that to get volume equal to okay. So now that we have a volume equation of that volume above where the dip line is, we can solve for the dip. So we'll take what we started with, and then we have a lot of cancellations here. And we get that the dip is equal to the centripetal frequency squared times the total radius squared over 4 times gravity. So now that we have that, we can bring back in the equation for total height, which was total height equal to height with respect to radial position plus the total radius minus the dip. And when we say the total radius minus the dip, we're talking about the total radius in regards to the total height of the fluid. And now we can sub in our new equations. So now that we have this, all we have to do is rearrange and we'll have that maximum angular frequency. And there you have it. That is our equation for the maximum angular frequency. We can spin the cup before our fluid spills out at radius r and height h. Thank you for watching.